stuff. Yeah,
That's
you get a little less efficiency and less capacity. The capacity doesn't really matter. The efficiency, the power, you can design around that. The efficiency is maybe a downside, but you maybe don't need great round trip efficiency if you're capturing something like solar that would have been wasted anyway.
Yeah.
On top of that, you've got the benefit of not using new batteries. You're saving some resources there, though it's not electricity source.
and
Yeah, you can go ahead.
That's really awesome that you guys are able to recycle the batteries like that. I know, like I'm really interested in like eVTOLs, like electric aviation type stuff, and I know there excuse me, there are regulations for a minimum battery efficiency that you have to have, like by the FAA, in order to be able to operate like some of these like these airplanes. And so if you're able to like recycle those batteries, like once they're, let's say, only 90% efficient, and move that back into the storage to like basically recycle the batteries, I think that's awesome. And one of the things I guess we were wondering is if you could talk more about the storage system that you guys have, like I guess
Well,
the charging stations. Right.
Yeah, so I don't know. So you haven't implemented any form of and because I remember so like your charging stations as of now are just basic charging stations, and they don't have any form of like new storage system at all. Yeah, or have you implemented? Yeah.
Well, like the nuts and bolts of it. Oh, sorry. Go ahead, Jim.
Well, I was going to say, it was just a proof of concept, right? The system's not running now. The specific value proposition for us and our customers, which are mostly fleets that run a lot of vehicles out of a depot, is twofold. One would be they could use the batteries they already own from vehicles, right? When those vehicles are at end of life, the batteries could be repurposed. The second value proposition is on like the facility basis, which is most of these fleets, if they need to charge 10, 20, 30, 50 trucks at a depot, that it takes a reasonable amount of power. It's not crazy. It's probably still sub-megawatt, but it's a few hundred kilowatts. And typically all the vehicles are charging overnight and they're all running during the day. So that electrical infrastructure that's built and installed to deliver energy to the vehicles is really only used overnight. And it just sits idle during the day when none of the vehicles are plugged in. And so the idea is, with those batteries, can we reuse that investment in the electrical infrastructure, right? Everything from the grid to the building, right, to the transformer, and the other work where they've gone in and put in maybe an upgraded electrical. Can we use that infrastructure during the day as well as at night? And that has a few benefits. Right, it's a better return on the investment of building the infrastructure, and potentially the way that utilities bill most commercial sites. That can also be beneficial because they're probably paying for the peak energy use that they use at night to charge the vehicles. And if they also draw that same amount of energy during the day, they're not paying any incremental demand charges for it. And so the idea was you connect the batteries to essentially the same power feed that's powering the charge stations. And you have this benefit of using the infrastructure a higher percentage of your 24-hour window every day. And then I guess the third benefit is if there's a blackout, you've got the batteries right there to provide power if the batteries have power, right? So you got to think about, well, how do we design a system so the batteries are going to be more likely to have power in the event of a blackout so that they can charge the vehicles, even maybe if the facility is unpowered.
Yeah, that sounds really cool. And I was also wondering, even if the batteries weren't, I'm assuming it would be way easier to implement it if you had new batteries. So I was wondering, like, well, first, what happens, I guess, to, let's say you have, a truck and it's a battery is no longer up to like spec. What happens to that? And I was also wondering, would it be worth like based on like how much you save, would it be worth to just place new batteries in place of like used ones and still have this energy storage system in your like company, and like how profitable, yeah, would it be, I guess? Yeah. Like would it, yeah, be worth, I guess, assigning like new batteries to for that purpose?
Sometimes, right, like stationary energy storage can be economical on its own. So you can have a facility and you can just decide, we're just going to put in stationary energy storage because the economics work for our facility. And it might have to do with how your facility uses power, how peaky are the loads, what time of day, what utility you're under, whether there are incentives, right? So there's a program in California called SGIP, which provides incentives for stationary storage. And so there are buildings that do that and the economics work. If you can use the same infrastructure for storage and for EV charging, the economics are going to be incrementally better, right? I mean, than doing either one of those on their own. How much incrementally better depends a lot on the site. New versus used batteries is I think the dominant driving factor there is how the cost of batteries evolve over time and where we are on the cost slope, right? Because if the price of batteries is being cut in half every 3 years, right, then it's almost certainly better to just use new batteries because, you have these batteries that are 6 or 9 years old. Let's say they're 9 years old and you paid, whatever, 8 times as much for them back then. And so, the incremental value out of those batteries is going to be very small. Like you can pay 1/8 to get a brand new battery system, right? If the price of batteries is only coming down 10% every year, then it's a little bit of a different game because in 9 years later, you either have this battery system that is worn out and it's at 80% of its capacity, but let's say but you can maybe buy it for 20% of its new sale price. And so you're able to get a lot more battery for your money versus if you go buy a new pack, which is not that much less expensive than it was 9 years ago, right?
Yeah.
So as the battery curve flattens, the battery cost curve flattens, I think second use is going to become more competitive with new battery purchase for that reason.
That makes a lot of sense. Yeah. And as of now, it's like starting to flatten out, as you say. Yeah. And
it is, yeah.
And do you think does that have to do with, I guess, like a stalling of actual technologies, or does it have to do more with, because we also did a good amount of research into the field of like, there's difficulties getting the materials to make these things, whether it's cobalt or lithium or whatever. And I was wondering, do you know anything about whether like it's the material shortages that are like keeping this price, like from decreasing, or is it, I don't know, or if you have any takes on that, or even if there's, your understanding, yes.
Yeah, I mean, having been in this industry a while, to me, it's amazing that people are talking $100 to $200 per kilowatt hour for batteries. When you think about all the work and process steps and materials content that goes into a battery cell, like it's just crazy incredible. It should be way more expensive, I think, but we just have such economies of scale. I mean, I think it's like we're just getting close to zero. That's the problem, right? It's like every little thing, things that were lost in the noise, like the transportation of the mineral ore, like we can make that more efficient. We can relocate battery pack plants to, where the minerals are, but then you got to transport the cells. Like, I mean, eventually the use of the vehicle isn't going to be where the mine is. So, refining, permitting, like overhead, like all of these costs of any manufacturing process are now a higher percentage. And so, you can't, I mean, we're never going to be able to build batteries for free. We're actually pretty close to free relative to where we started. I mean, it depends, you can't quite look at it exactly geometric or exactly linear when you look at these curves, right? It's kind of somewhere in between. They'll continue to come down, but if you look at the linear rate of price reduction, it certainly is going to decrease just because otherwise we'd have to give them away in 2 years. But if from a geometric rate, they're going to keep coming down, but I think you're just going to have these basic floor costs that come with any production of physical stuff that's going to start to be more important.
That's really interesting. Yeah, because I don't know, the kind of vibe has been like it's difficult to get these like lithium ion batteries. I don't know, has that been the case or no?
Well, yeah, there are various materials that are difficult to get, and they go up and down. Like the nickel markets have been crazy. Cobalt's quite expensive, but the batteries we're using now don't need cobalt. So,
I see.
you know, technology tends to work around any one particular constraint. Like we can kind of just develop around it. Lithium is another one, right? But there's actually a lot of lithium in salt water. So, but it's hard to extract right now. But who knows? Maybe we'll figure out a way to do it easier. I think I'm kind of an optimist, like when it comes to any particular shortage. I think they're mostly just short term.
I see.
Like I don't think we're going to run out of lithium on this planet or anything like that.
Cool. Yeah, thanks for that. That was a great response. So I guess like one of the things, like while we're talking about like lithium ion batteries, like I guess what made you guys like push or go in that route of like batteries? And I know like also, have you considered like different materials? I think we were investigating batteries that are compatible with like solar panels, and it seems like gallium arsenide was a battery that seems promising at least. So I know lithium ion batteries are most common in the industry, but have you considered other batteries, other materials, things like that?
Yeah, probably more than most. The demo we did at MUD was actually not lithium ion. It was sodium nickel. I know I dropped out for a minute. Maybe Josh mentioned that or Henry, but so that's a different chemistry. It has pros and cons versus lithium ion. Sodium nickel is nice because your mineral content is just table salt and nickel, right? Like super abundant minerals, obviously highly purified and such. But the downside is that it's very low power. So you got to heat the battery to get any reasonable amount of power out of it. I think lithium ion, like the family of chemistries around lithium, which includes NCA, NMC, LFP, LCO, LTO, right? These are all various lithium-based chemistries. That family of chemistries has clearly come to dominate the energy storage space, right? Lithium has kind of a unique place on the periodic table. You know, you can build very energy-dense systems with lithium, but it's really like economies of scale, right? The scale around these lithium-based chemistries is just so much larger. Sodium nickel, it's good technology, but it just doesn't have nearly the scale. It can't really compete. So we've looked, you know, and there are new chemistries coming out. Like some of them are in the lithium family. Some maybe aren't. There's a lot of talk about like solid state lithium batteries, you know, where, you know, maybe you are moving to like a silicon anode lithium battery, right? And there's interesting work there. And, you know, it will continue to push up energy density, but chemistry doesn't follow Moore's law. Chemistry plods along at a more linear pace. So I think we'll continue to see better, but for energy grid storage, you have a slightly different requirement set. You care a lot less about size and weight. So therefore you care a lot less about energy density and power density, right? Like you probably have a lot of space and you don't care how heavy it is. So then I think that does change the economic, like it changes what solution you might want to implement because of that. Right? Yeah.
Yeah, I was also interested because you mentioned how ultimately the clinic project ended up not actually coming to a like successful conclusion, I guess. And I was wondering if you could, I guess, expand on what was the thing, I guess, the limiting factor or what made it the most difficult. I know that there's like a mismatch between like the power or voltage outputs, and you had to kind of like match those. But I guess what was the main, what are some of the main like problems when it comes to reusing batteries, right? Because I think if we're able to, it would be definitely helpful. You know, it would maximize how much energy storage we would have without even adding any extra production. So I don't know if you could, I guess, explain. Yeah.
I think I would kind of point the reasons the project were difficult were, and I mean, all that are kind of reasons that battery storage, like reusing battery storage, is difficult. If you there's a lot of hardware that has to be designed to implement any battery that you want to do. So like you have to design all your wiring and your kind of your structural interface for holding those batteries. And then you have to design the software or whatever firmware like stack that you're going to use to control those batteries. And say you have a good supply of like one battery, but then you want to switch to another battery, and you have to, I don't know, you get a new, and then you have to redesign a lot of that hardware and software. So I think that we could have been more helpful, or I personally feel like it could have been more helpful, at least on the hardware side, because that's just something that's so foreign to like I know when I was in college, high volt connectors, high current grid stuff, like all that is just, that's so new, and there's a lot to learn there.
Mhm.
But if you want to get to the really juicy bits of like seeing something operating and testing it and actually doing some like storing some energy and releasing it later, we could have accelerated that.
I see. But it was more like the students were kind of like very, like they're experiencing this new project. And it's not more of like, would you describe it as a difficult thing, period? Like not besides just like for college students, but like would it be, how possible, I guess, would it be to implement if like, I don't know, if you set a group to do it, like, is it just a difficult thing, period, Yeah.
There are a lot of interfaces, I think, and so it's definitely not impossible. Like
Mhm.
it can be done. The tricky part is getting a grasp on, say, like how do you talk to the battery, and then what do you tell the battery to do? How do you get that communication loop to coordinate with the other two batteries, or however many batteries you have? And then you've got to coordinate that system with the inverter system, coordinate that with the, I'm forgetting a part. Whatever the other part of the system is to get you to the grid.
Well, there's the breaker, and then the current or the power meter,
Yeah.
and like the grid itself, like what does the grid want right now, or what does your building want right now?
Yeah.
Yeah.
So like there's a lot of moving parts, and it becomes it's a relatively complex system, so it's definitely, yeah.
I see.
The Department of Energy uses a term called techno-economic challenges, right? Because it's not purely technology and it's not purely economics. It's really the meeting of the two, right? It's like you have to invest a lot of engineering to develop and validate the system, especially if you're using used batteries, because every used battery, 2 used batteries that come out of different vehicles from different manufacturers are going to have very different interfaces, which means there's some development and probably a lot of validation, right? Validation is always more than development. And so you have to then kind of figure out where you are on kind of your business case to say, I need to invest this much engineering and validation time, and what's my supply of batteries going to be? Like, how much do I need to invest per system? How much can I invest once and then have it scale across systems, right? And I think what Josh and Henry are saying is like that interface complexity is pretty high. One of our battery suppliers now out of Michigan is developing a grid-tied energy storage system that uses the same battery packs we're putting in our vehicles. And what they're doing there is they're tearing the whole BMS off of the battery pack and putting on a new BMS, right? Because that's one way to solve the interface problem. But they can only do that for their own used battery packs, right? Like they'd have to develop a whole new BMS now if they wanted to accept a different battery pack. The only really technical challenge, which isn't that hard to deal with, is as these batteries age, there's some differential aging. And so having the batteries operate in parallel can be a little bit challenging. That's mitigated by using like separate power front ends per pack, or you know, having a battery management system that can accommodate that, like our battery supplier is doing. So there are ways around these. There's no fundamental technology challenge here. It's really more around, is it like, does the business case work?
Mm. And you mentioned, what was the name of the company that was trying to implement it?
It's a company called One Battery, Our Next Energy, ONE, out of Michigan.
Mm-mm. And have they been successful, or are they still trying?
My understanding is that they haven't implemented any systems yet, but they have a like preliminary, they're in the middle of doing that design, and they have some contracts to implement these. So they're planning to implement them.
Mm-hmm. And like, yeah, you can go ahead, Gabe.
So I guess like another thing, I just wanted to ask you guys, and maybe this is more of a question for Jim. I guess what are like your main motivations for like the company itself? Like, is it more to reduce cost or like reduce CO2? Yeah.
We're here to free fleets from fossil fuel, right? So the primary goal is that energy independence, right? And so what that creates are economic advantages, both in terms of lower cost and also lower risk, and certainly it creates some sustainability, environmental advantages as well, especially if the grid is getting greener, which it definitely is across the country, and especially in some of the places where we have a lot of vehicles deployed, like California. So yeah, there are a lot of drivers for why fleets are buying electric trucks right now. Some of them are regulatory, some of them are economic, and some of them are sustainability.
Okay, cool.
I'm gonna, I guess, show a bit of my personal philosophy here. One of my chem profs, he had forget his name right now, I'm sorry, a phrase or like an anecdote that stood out to me was like when he was on a research team or something, they would spend a lot of effort trying to convince get funding for their solar panel, quantum dot solar panel, solar energy research. And he came to the realization at some point that like no matter how much like potential you can show that your project has, or that your research or your technology has, because of the system that we work in, the systems that we're in, like you just have to prove that it's better than the alternatives, in terms of cost, essentially. Like you have to prove that you can provide a better truck for the price. Otherwise it's not gonna get any ground. So like when it comes to like, are we doing it for carbon reduction, or are we doing it to save money on energy costs? They end up like we're intentionally intertwining them. Like if we want to reduce carbon emissions, the effective, like our way of doing that is by making it cheaper to use vehicles that, or more attractive to use vehicles that do reduce those emissions. So like we're combining the two things.
That makes sense.
And I think that makes
sense. Was it Prof. Ben Reisnick? Do you know?
I think so. He's the quantum dots prof, right? Okay.
Yeah.
Cool.
Yeah. So no, that kind of mixes like blends into another set of questions that we wanted to ask, and it's like, yeah, how do you get these things out there? You know, you have like, I don't know, let's say we develop a research proposal, right? How do you go about I don't know. And yeah, I guess that would be a valid answer, make it profitable. But I don't know. And I also wonder, like, Jim, how was the process of founding this? You know, like you had to have some start, you know, some initial funding. So yeah, I don't know. Like you have an idea, you wanna like initiate it, you know, how do you get it started? How do you spread? Yeah, like yeah.
Come see my guest lecture on April 14th, 13th, 14th
Yeah.
at Mud. You can learn all about that. Now I need to tell you what day it actually is because I think it's the 13th. Yeah, on the 13th. I'm doing a lecture for Cash Gokley's, Professor Gokley's class, and it should be fun that evening. It's like a seminar. I think it's open to all. If it's not, I'm sure that I could get the invitation extended. So I don't want to spoil that, but I'll give you a few highlights. So certainly, I think like it depends a little what your final goals are. Like in my case, I wanted to free fleet from fossil fuel, start and do that by starting a company that could sell the trucks that they would. And actually, I didn't even want to sell the whole trucks, just the systems, be more of a parts supplier. But Motiv started with a grant from the California Energy Commission. And that is actually a really good place to start for a lot of projects. You know, if it's purely research, you can also look at like National Science Foundation and, you know, other kind of research, DOE kind of places for grants. But if you're looking to bring something to market and you're in California, CEC is great. Like out of grad school, no experience. We were able to win a $1.3 million award, something like that. Just kind of incredible. I don't know why they ever trusted me, but that allowed us to develop the tech a little bit, and then raise some money, right? You can certainly seek private investment there. You have to have a compelling business pitch story. Your third option is like bootstrapping, right? You just like find a problem that you can solve and you just figure out how to solve it. And, you know, maybe that means you have to eat ramen for a few months or whatever. Like, you know, you just cut your costs and you figure out how to do it. And then, you know, you get paid by that one customer and you can use that. And, you know, maybe even they'll pay you in advance, maybe, probably not, but maybe, right? And then you can kind of just bootstrap and work from the ground up. And so they're all valid sources. You know, I think a lot of starting a company is determining your resource plan, right? Like where are the resources coming from? And then probably the only thing more important than that is your customer plan. Like, what are you selling? Why do they want to buy it? And what makes you think that they're willing to pay for it? And how much are they willing to pay? Right? And then can you build it, develop it, and sell it for less than what they're willing to pay for it? Right? So, yeah, it's there are other ways too. You can do like the nonprofit route, right? Or more of like a policy kind of influence thing. Certainly policies and regulations play a huge role in our industry, driving demand, right? So that's a big part of creating change in the market, is also working that angle on kind of policy regulation.
Jim, where do things like the
Yeah.
ACT Expo come into this? I haven't been to one, so I don't know what it's like. But it seems to me like something.
Tell me more. Like what are you thinking, Henry?
I don't know. Is it a place where you could get a booth with your project and demonstrate it to people? I'm not sure. Like if the idea is to like, how do you get your product out there?
Got it. Yeah. So like, how do you meet customers?
Yeah.
Right. And something like ACT Expo is a great opportunity for that, because you find like a trade show and you get like little, you spend what seems like a ridiculously large amount of money to get some little tiny booth in the very corner. Right. It's like the early days of Motiv. Now we spend an even more ridiculous amount of money to get a bigger booth, not quite in the corner. But you get business, you find customers that way. You're demonstrating your legitimacy, right, with stuff like that. But the advantage you have is like a college team is a lot of customers who wouldn't otherwise talk to you if you just say, hey, I'm with Harvey Mudd College and we're investigating a potential business idea. they'll be like, oh, sure, we're happy to take your call. Like play the college student card, because that's a good one, right? It immediately gives you a certain level of legitimacy, which you should leverage. Yeah, but like the whole, how do I meet customers? To Henry's point, yeah, that's one of the most important things you do if you want to start any kind of new thing. You can't just assume that you know what the customers want, right? Like a lot of work goes into validating the customer value proposition.
Cool. And I guess like similar to that, we also wanted to know like what were some of the barriers that you faced like when trying to get your ideas out there. Obviously like money, but it seems like
you had that covered.
Yeah, I had that covered. And also like I'm opening this up for Henry and Joshua. Like what are some of the barriers that you guys have faced like as engineers in the company?
Can you ask that question again?
Oh, sure. Yeah. I'm just wondering like what has there been like any like barrier in your time at Motiv, like as an engineer, like just in general?
Okay. Go ahead, Henry.
Okay. I'm not sure if I've got any barriers that at least I would imagine are unique to renewable energy or clean energy vehicles necessarily. One of my kind of persistent gripes is dealing with code that hasn't been maintained or refactored on a regular basis, or documented. And it's not like the entire thing is always just mystery code that spaghetti, you don't know how it works. But I guess barriers that I run into that are my own, not fault, but my own barriers would be, just deciding how to approach a problem, designing, like, how do you want to design a system, right? Right now I'm working on a automated test suite for one of our new boxes, and coming up with how to approach the design is it can be a challenge, especially when you've maybe got a couple of competing preferences in terms of how do you want to structure this program. Do you want to be able to log every bit of every test result incrementally, or report it all at the end? There's all kinds of design decisions, and I guess what I've gotten around it, and this is more for like the electrical types of questions that I end up facing. Like a year or so out of college, I came to the realization that like faced with an issue or a question, like a problem statement, you at some point just realized, oh, I can just do this. Like this isn't anything different than like a set of a set of E82 problems wrapped up a little differently and without anybody like directly grading your answer. So like if you have an idea of how to make a circuit that switches a resistor in and out of parallel with another part of the circuit, like if you have an idea of how to do that, then you can, you're probably right. So you try it, and if something doesn't work the way you expect, you iterate on your design. So I think that overcoming that barrier, I guess, is just a matter of building some self-confidence in your engineering and programming and design capabilities. It's a little waxing poetic, Josh.
That's great to hear, especially as an engineer.
Yeah, Gabriel is looking for the encouragement. Yeah, yeah, you can go ahead, Joshua, if you want. Yeah.
Yeah, I think to go off Henry or just kind of summarize it, mud, even if you don't, at least I know going through mud, I didn't think I understood everything I learned, but at the end, you will have all the skills you need to do pretty much anything you want. So, and things will come back to you. And even if you didn't understand it when you were taking the class, it might make more sense when you see it in the real world. The question, as far as the question, some barrier that I've encountered. I don't know. I can't think of a good one right now.
Yeah, no, it's okay. It's okay.
Yeah.
I mean, I guess what's
Your
I don't know.
your CTO coming in at the last minute and changing requirements or making design changes on you. No, that never happens, right?
Those are fine. Those are fine.
Spoken well. I'll pay you off later. You know, as the company grows, there are different types of challenges. Like to Henry's point, I remember developing a resolver driver circuit once, a while back at Motiv, and it's like an H bridge to create a sine wave, right? And you're feeding a resolver, which is like an inductor and resistor kind of, and like the current and voltage waveforms weren't aligned. And I actually went back, like opened up my textbook, like did the math and determined how I could change the like switching duty cycle to make the current and voltage align, like better power factor, and like got some totally non-intuitive results about what I needed the duty cycles to be. And I'm like, okay, well, I'm going to trust the math. And I like put it into the code and ran it, and it worked perfectly, like the first time. I remember this because out of 13 years of being at Motiv, it's the only time where like something worked perfectly the first time. And I was like just so thrilled because the math just worked. There's like just trust the the basic physics, and it just just happened. So, but I mean, there are all sorts of challenges that you face, like as you're trying to bring a product or to market or create a value proposition for a customer, and as the company grows, right? And so there are all sorts of growth challenges. So. Yeah, but that's part of the fun, I guess. I don't know. I mean, if you have more specifics, I could try and answer it. Otherwise, I think Henry and Josh gave you a pretty good summary.
Yeah, no, I think they're great answers. Yeah. And it's like, yeah, I guess the process of being an engineer, which, yeah, pretty cool. I don't know. I also just wanted to ask some like questions that I'm just like generally just curious about. So I don't know. Right now we're considering like hydro pump as a form of energy storage, right? And I was wondering, like, if you guys know, like, what's the limitations, I guess, on how far power can travel, because like certain states, I don't know, they get their energy from over here. I don't know, like, what's stopping us from having like one big hydro plant and then just powering like all of the US? I don't know, like, I guess the physics or I don't know, like.
I love pump store hydro. It's efficient. First time I was ever exposed to pump store hydro was my engineering professor from Mud. He's retired now, but Joseph King took me rock climbing at Courtright Reservoir. And if you ever have a chance to visit Courtright and Washon reservoirs, it's a very large gigawatt scale pump store hydro site. You have the two lakes, Courtright above and Washon below, and they bored a giant hole through the intermediate granite, and they connected it with, I think it's like 4 300 megawatt turbines. They can pump the water up to Courtright and get the energy back when it goes down to Washon. And it's a great system. It stores a ton of power. And high voltage power lines are very efficient, like shockingly efficient for moving energy from one place to another, like far more efficient than any other way that we have to move energy from one place to another. So the biggest problem with pump store hydro is to have any kind of scale on it, you're kind of relying on geography, on Mother Nature, right? Because you can't like very easily build a lake that's any reasonable distance from another lake and hundreds of feet above it, right? Like the amount of earth moving is completely impractical. So you're kind of relying on Mother Nature to find places in the geography of the land where you could have two reservoirs that are appropriate, distance and height. And there aren't a ton of places where you can obviously do that. And my understanding, this is like an offhand comment I heard from someone who wasn't exactly an expert, but knew about it a little bit years ago, is that most of the places where you can economically build pump store hydro, it's already been built. It's already done. So that's kind of my take on pump store, because when I first learned about it, I'm like, this is amazing. It's like simple technology, the efficiency is great. Like, what's the downside? But I think it's just availability of spaces.
You talked about building one just in the US that could power the whole US.
It's like a giant.
That would be so big. It'd have to be in the mountains somewhere, right? I was thinking, oh, well, you put it in the middle of the country, right? But then you think of Kansas, you're like, it's not really gonna hold your two lakes very far apart from each other.
Yeah.
So you gotta go look at the Rockies, but it's hard to build that. You
can always go underground, can't you?
You need a pretty big cave, a really deep, big cave.
Yeah, but I mean, so I guess the limitation is, well, I mean, also just generally speaking, like, if I did have like something in California, let's say we put some reservoir in the mountains, like how far can that electricity, I guess, like travel? Like, what are the, like, I don't know if do you guys have any idea? I'm just curious. Yeah.
I think
it's the water that's the problem, right? Like, if you've got to keep the lakes close together, because otherwise your efficiency of pushing water back and forth, that goes down pretty quick, right? So you need the tube between them to be pretty short to have efficiency. Moving the electricity, you can move that across the country, not
really
that hard, right?
Oh, that's crazy.
Yeah, high tension power lines, do a million volt DC line like the one between Washington and Southern California that runs through the desert. If you're ever out driving there, look for the high tension line where there's only 2 power lines instead of the normal 3. That's it. Million volt DC. It's plus 500K, minus 500K. Amazing piece of engineering done way too long ago for what it did. It's incredible, right? And super efficient. So yeah, like high voltage, high tension lines generally, and especially high voltage DC lines are super efficient. You move a lot of power.
I see. That's crazy.
That's awesome.
Is it only 1,000,000 volts?
Yep. And it has a backup mode where they can take down one of the lines and return the power through the earth. They have like huge copper meshes in Washington and in Southern California, like the ocean, and they can return all of that current through the earth. Like, obviously it derates, but then they can service one side of the line at a time. Crazy.
That's crazy. And how long ago?
It was built in like the 70s. It's incredible.
Crazy.
Yeah.
Crazy.
Been upgraded since, like, they were using, I don't know, thyristors back then. Now it's probably like optical turn on FETs or something. But, yeah.
That's pretty cool.
They still need like 1,000 amps to flow a gigawatt.
Yeah, gigawatts.
I guess 1,000 amps isn't that big. Like, we almost do that on our trucks. So if you can build a whole
you can
tower,
have a conductor that big around.
Yeah. I go to like a 1 billion volts. I guess it's kind of hard to generate 1 billion volts.
This is so well, I think that like the line of questions, I guess. Yeah, you guys have answered everything. So yeah, thank you guys a lot. And yeah, I mean, I've enjoyed it. So yeah.
Me too.
Well, good luck on your project. This is a great topic. We think about it a lot too, obviously for, vehicle second life and kind of the synergies with the depot, but also the vehicles themselves providing grid storage. People call that vehicle to grid. Some of it, I think, doesn't work that well. The economics don't work well, but if you do it the right way, I think it could work really well. So solving the grid challenges, there's going to be a lot of innovative solutions that are needed for that. So yeah, happy to, would love to see the research paper when you guys are done with it, if you don't mind. And yeah, good luck.
Yeah. So actually, so for the class, it's there's like going to be like I think it's going to be on alumni weekend or like around that time period. So I mean, if you guys want to, like, I think we're going to do in person and virtual. I think so. Yeah, like presentations of all of our projects. So I don't know if you guys would want to attend. Okay. We could send you the links, or if you're coming this alumni weekend, I don't know. Yeah. Yeah.
Yeah,
So yeah.
well, please send the links. Yeah, and like I said, you're both welcome to attend that the lecture
Yeah.
if you want to hear more about Motiv's story on the 13th. So, yeah.
Oh,
Okay,
well,
yeah.
thanks so much, guys. This was not only really informative, but also really fun and great to hear some engineering.
Yeah, reinforced Gabriel's desire to be an engineer.
Yes.
Yeah, yeah.
If you guys have-
You can do a lot of good as an engineer for sure. So,
Yeah, it was
Great.
quite a decision for me. Engineering CS, yeah, but I'm already too far.
you can do a lot of good in CS too. CS is great too. I
Self-engineering.
mean, you know,
Different.
we can't do very much of our engineering at Motiv without CS in there too. So yeah, they need each other in my opinion.
Yeah, yeah. But you know, so thank you guys so much, and yeah, I hope you enjoy the rest of your days.
Yeah.
Thank you.
Thank you.
Great, thanks.
Stay in touch. If you ever want to chat
Henry and
again.
Josh, I'm hoping you can join for that other meeting invite I just sent you. I know it's kind of last minute, but all right.
Oh.
Thanks again.
All right.
Okay. Bye.
See you guys.
Good to
Thank
meet
you.
you. See you.